Good evening everyone. In this video, we will be performing a concrete cylinder compression test using the concrete damage plasticity CDP material model in Abaqus. We know concrete behaves very differently from metals. It is strong in compression but relatively weak in tension. And once crack begins to form, its stiffness starts degrading. Because of this nonlinear behavior, a simple elastic plastic material is not sufficient. The concrete damage plasticity model is specifically developed to capture concrete crushing in compression, cracking in tension, and stiffness degradation during loading. So, by the end of this analysis, we'll be done by creating a concrete cylinder geometry, assign the concrete material property, applying the load and boundary condition. We'll be creating a specific mesh for this model. We will configure the nonlinear analysis detail. We'll monitor convergence using scaling, and we'll check upon the results after the analysis gets solved. So we'll start by creating the specimen. Create a new mechanical scenario and begin with the new part. The specimen used here is a standard concrete compression cylinder having a specific diameter and a specific height. Select cylinder from the primitive geometry tools, enter the required dimensions, confirm the geometry. This cylindrical specimen now represents the concrete sample that will undergo axial compression. At this stage, the geometry is intentionally simple, allowing us to focus on the material behavior rather than the geometric complexity. Next, we'll create the planes required for partitioning. Reference plane we know helps us divide the model into regions that improve mesh quality and numerical stability. We'll create a datum plane passing through the center of the cylinder. Depending on your workflow, you can just additionally add planes and create perpendicular to the cylindrical axis. These planes will later be used for the solid partitioning. Good partitioning is especially important for nonlinear simulation because it provides a more structured mesh and improved convergence. Now we'll just check upon the datum planes. We'll split the cylinder into multiple regions. The objective here is to change the geometric physically, and it is also used to improve the mesh distribution. Structured partitioning generally produce better quality elements, reduce element distortion, and improve the accuracy of strain and stress predictions. A well-partitioned model is one of the keys to obtain a stable nonlinear solution. Now, after we get this done, we'll open the material library and we will choose the model for our analysis. Here we are using a concrete CDP, as in concrete damage plasticity model. We'll create a new material. The first property we'll assign is a Young's modulus, Poisson's ratio. These definitions are very initial in the linear elastic response before damage begins. So we will include dilation angle, flow potential centricity, and K ratio with viscosity parameter. These parameters control the plastic flow and damage evolution of concrete. Next, we'll define the compression hardening. This describes how concrete gains strength and then softens under compression. Compression damage you can also define. This representation of reduction in the stiffness caused by crushing. You can similarly define tension stiffening. Concrete has very little tensile strength. Instead of suddenly removing tensile stress after cracking, tension stiffening allows us to gradually transfer the stress, improving convergence and representing the realistic behavior of crack. After the tension gets defined, we'll define the tension damage. Tension damage is also important because this captures the stiffness degradation after tensile cracking. Together, these four datasets allow the CDP model to accurately represent cracking, crushing, and irreversible damage. Now assign the material to the concrete model. Assign the material, and after it gets assigned, we can just say that our solid cylinder is now a homogeneous material, or the isotropic material has been defined for our model. We can just create an assembly. We can create independent instances of the cylinder. The assembly represents the physical placement of components within the simulation. Since only one specimen has been used, no additional positioning is required. So the cylinder remains centered in the global coordinate system. Now, after we get all of this done, we'll apply the boundary conditions. I'm mentioning again, you can create an independent instance of the cylinder. The assembly represents the physical placement of component within the simulation. Since only one specimen has been used, let's focus on this line. You don't need any additional positioning, or any additional positioning will not be required after we define the cylinder position at the center of the global coordinate system. Together, the four data sets, that is tension damage, tension stiffening, compression damage, and compression hardening. Together, these four data sets collectively allow the CDP model to accurately represent the cracking, crushing, and irreversible damage. So, after applying the material, creating, if required, a assembly, now we'll get this done after we apply loads and boundary condition. So just let me complete this procedure, and then we will apply the loading condition, or I can say boundary condition. As you can see that CDP or the concrete damage plasticity model has been defined by using dilation angle, flow potential eccentricity, K ratio, and viscosity parameters, and obviously Young's modulus and Poisson's ratio. The first property I mentioned was the elastic behavior. As the load gets applied on the cylinder, we need to accurately capture the behavior of the concrete. So in that process, we need to go with the elastic behavior, and then we will get this to the plasticity behavior. Now we will apply loads and boundary condition. So after creating a reference point above the cylinder, couple the top faces of the cylinder with this reference point using a kinematic coupling. As we know, coupling is a procedure to apply loads on a specific point, and then that point will represent a total number of faces, or n number of faces, by which we are referring it. So here we are using kinematic coupling constraint. This ensures the load is distributed uniformly across the top face. Next constraint would be my bottom face. I'll fix all the translational degrees of freedom through which I can represent the testing machine pattern holding the specimen in a place. Now I have created a coupling that is kinematic in nature, and I have placed a constraint on the top and the bottom face. We'll apply the compressive load. Instead of applying force directly, we'll go from the displacement control loading. That is, by applying some displacement or allowing some displacement in the concrete cylinder, I'll apply the load. I'll not randomly put a top load on the top face, but I'll allow some displacement control loading that is generally preferred for nonlinear concrete simulation, because it provides a better convergence during post-peak softening. So after applying a downward displacement at the reference point along the cylinder axis, this loading method specifically allows the analysis to continue even after the damage initiates, because our goal is not to just capture the damage, but to actually capture the real behavior of the concrete that happens after the damage. After the damage has been done, we'll capture that behavior also. So after fixing all the translational degrees of freedom by constraining the top and the bottom face, I'll apply the load in the distributed manner, or on the face distributed uniformly across the top surface. There are multiple options in Abaqus through which you can capture the realistic displacement or the realistic loading condition by clamping it at the top face or the bottom face. You can just apply rotation, you can just apply bearing constraint as well. Now I'll define the step analysis, or I'll define the analysis step. After creating a static general step, since the problem contains material nonlinearity and progressive damage, we will be going for the non-linear geometry, that is also known as non-gem. We'll adjust the increment setting. We'll choose a small increment time, specify appropriate minimum and maximum increment size. I'll allow automatic incrementation. So these settings help Abaqus maintain convergence while concrete stiffens changes across cracking and crushing. So cracking and crushing is very different process altogether. Now I'll request the desired field output such as stress, strain, displacement, plastic strain, damage variables, and the reaction forces. There are multiple other simulation studies as well that you can run in Abaqus or in the package as I conclude. Those packages are called as Tosca for optimization, and there is one more. These output will help in the post processing and evaluating the structural response. Now I'll generate a mesh. I'll create a mesh by assigning the element type. For 3D solid concrete model, I'll reduce integration break element because these are commonly preferred. Seed the part using an appropriate global element size. A finer mesh improve accuracy but also increase computational cost. So I'll click on the generate mesh option. I'll inspect the mesh quality carefully, check for the distorted element and abrupt transition sizes. A good mesh quality is essential for obtaining reliable damage predictions. So I was mentioning there are multiple other simulation studies that you can run into Abaqus with other solvers as well. Tosca for optimization, Abaqus for structural. There's another package in LS-DYNA ANSYS that you can also use for running this same simulation. Now after the mesh gets generated, we'll go for scaling. So scaling is used to allow the non-linear solver to better handle the stiffness degradation. After the mesh gets done, we'll jump upon the scaling process. So optimization is overall used for getting the best design output that you can get under the consideration of the input that you have applied. Scaling we will be performing with some parameters. Because the model experience severe convergence difficulties, we'll carefully adjust the stabilization. And these stabilization are called as the parameters for scaling. We'll review the scaling parameters because if a model experiences convergence difficulties, we'll carefully adjust the stabilization parameters, and only those parameters can help us solve this nonlinear simulation. Because excessive stabilization may artificially influence the structural response. Therefore, scaling should always be used conservatively. Conservatively as in by applying the parameters manually and not rely upon the software alone. The objective of the scaling is to improve numerical stability while maintaining physical accuracy, because nonlinear simulations are very slow in nature or very slow in solving, because at each iteration there might be solving n number of equations, and due to which convergence error can come up. So scaling is used. Now after getting this model scaled, we'll check the final model. Before running the analysis, we'll perform a complete model verification. We'll check the model tool. We will verify some parameters, that is missing material assignment, invalid constraint, undefined interaction, mesh quality, loading condition, boundary condition, step setting, and solver warnings. Resolving the warnings before solving saves considerable debugging time. Once the model passes all checks, submit the analysis for the solver to the solver. After completing, we will evaluate some parameters or the outputs that we requested, that is compression stress distribution, damage evolution, plastic strain, deformed shape, reaction forces versus displacement graph, concrete crushing regions. Now, these results provide insight into the non-linear behavior of concrete under compression and demonstrate how the concrete damage plasticity model CDP captures both stiffness degradation and material failure. After this analysis gets solved, we can conclude that this particular simulation on performing a concrete cylinder compression test using the concrete damage plasticity model, we have covered a significant amount of workflow from geometry creation and material definition to nonlinear analysis setup within the Abaqus, within the same environment of a software, in which we have done meshing, convergence considerations, and model verification. So this complete package of Abaqus can help us design better or bypass the guesswork that creates a lot of buffer within the design process. So I would like to thank you for watching this video till the end. I hope this tutorial helps you better understand the nonlinear concrete simulation using the CDP model. If you found it useful, consider exploring more additional studies on this channel. Thank you so much. I'll be posting more about reinforced concrete, cyclic loading, and confinement effects using the same material model. So thank you so much for watching this. I hope I should start CFD also, but I'll update on this channel only. Thank you so much.